Today we have Jack Guo, and he has a fantastic looking presentation lined up for us on disaster resiliency and embodied carbon. But to begin, just a little bit about the Carbon Leadership Forum. So the Carbon Leadership Forum, or CLF, is a program based out of the University of Washington that aims to radically reduce the embodied carbon in buildings and infrastructure. So here in Vancouver, this is the local Vancouver hub, and we are led by our two co-chairs, Zara Tashnizi and Jeremy Field. Zara is the Senior Advisor at Mantle Developments, and Jeremy is a Senior Sustainability Advisor with Integral Group. We have a group of fantastic volunteers who organize monthly events like these that aim to empower industry professionals through sharing knowledge, ideas, experiences, and challenges. You can sign up either to our local Vancouver hub or to the main hub or the main central bodies, and the two links are on the screen there. We do have two upcoming events. One in November 26th, which is a partnership with CEBEX, and we'll be sending out information on that shortly. And also, we're aiming to have an end of year in-person social, which is possibly a risky aim. More details also to come, but save the date, December 2nd. And my name is Caroline Butchart. I'm a specialist engineer with FASTNet. We are structural engineers. I'm a member of the sustainability team and also a volunteer with CLF Vancouver. So I will be the moderator and the host for today. If you do have questions, please do enter them into the chat. We'll be monitoring those questions and we'll revisit those at the end. And also we encourage a good Q&A discussion at the end of this presentation. So as I mentioned, the video, this webinar, it's being recorded and we will post that online in the next few days. And with that, I will hand over to Jack.
Thanks, Caroline. See if I can share my screen. Is it popping up for everyone?
Not yet, no.
Okay. Okay.
There we are.
Okay, great. So thanks a lot for the introduction. Hello, everyone, and welcome. Just before I start, I'd like to probably apologize in advance if I sound funny on your screen or iPad or iPhone or whatever. Seasonal allergy got me this year, and I thought I was going to get off easy because I'm staying so much indoors, but apparently that's not the case. But welcome to this CLF Vancouver presentation on disaster resilience and sustainability. My name is Jack Guo, and I'm the principal at Kinetica Risk, and we are a specialized consultant on assets resilient decision support. And truthfully, I've probably contemplated this presentation, and Anthony and Zara will know for quite a while now, and I thought this is an interesting topic to explore, despite possibly being somewhat unrelated for some of you at first glance. So the talk will be on sort of the overlap between sort of two thrusts of climate change that we always talk about, resiliency and sustainability. And what I will focus more on is obviously sort of the emissions reduction aspect or the embodied carbon aspect of things, and specifically examining some of the tools that helps us look at these problems in a more integral way. And I'll go over the ideas behind them and present some examples when they're being used in real practice. But I do want to stress at this point that I don't think that this is the only aspect that's of relevance. And I think there's probably a bigger underlying theme is that there should be a more holistic decision framework that incorporates both aspects, resiliency and sustainability when it comes to real asset planning and investment, particularly with the challenges that climate change poses to the long-term impact of our built environment. So without further ado, I do have a couple of slides that just goes over a quick introduction of what Kinetica Risk does, just to provide a bit of context of why am I talking about this, and coming from my perspective. So in one short statement, Kinetica Risk helps owners and stakeholders of critical facilities embed resiliency using risk and mitigation analytics generated from science-based simulations. So we spun off a number of years ago from the Center of Resilience in Critical Infrastructure at the University of Toronto. And we're now headquartered in Toronto, and we have a satellite office in San Francisco. So the bulk of the work that we do in sort of asset portfolio resiliency focuses more on designing highly stakeholder-oriented decision support for different types of physical hazards. This includes, geological hazards like earthquakes or climate-related hazards during the different stages of the asset management cycle. So this will include risk management strategies, CapEx and OpEx planning, as well as things like business continuity planning. So what we do is that we combine, a lot of the scientific models and literatures out there on climate and catastrophe models with high fidelity engineering and risk analysis on real asset portfolios. And there's a multidisciplinary team behind me that does all these. But personally, my background is in seismic risk, and you'll see that in a lot of today's presentation, which really focuses on example coming from earthquake engineering, which is one of the most relevant hazards in the West Coast. So enough about Kinetica risk. I think it's time to bring it back to the topic. Why should we be discussing resiliency and sustainability together? That's not really a rhetorical question, but a genuine one, because a lot of my practice, honestly, my feeling is that both of these aspects are sort of in their own silo. They're well encapsulated in their own practice group. But but I do encounter cases where a lot of the times that you should be considering both of them. And when I say sustainability, by the way, in the context of this presentation, 90% of the time I mean embodied carbon. And I realize that sustainability is a much bigger umbrella covering a lot more aspects than just carbon emissions. And that's but perhaps it's somewhat intentional in the sense that I wanted to convey there's probably more to just the embodied carbon, but the embodied carbon aspect is one big one, and that's our focus today. So I wanted to basically start this discussion with a bit of sort of a thought starter. So if you start to contrast the qualities of sustainable construction versus resilient construction, what do you tend to think about? On the one hand, for sustainability, for sustainable construction, we are typically interested in lower operational carbon, lower embodied carbon, lower energy, recycling buildings, reusing them, extending their life at the end of the life. On the other hand, when we think about resilience construction, typically it starts with speedy recovery from major shocks. That essentially is what resiliency means. And stemming from that, reduce economic loss, risk, reduce business interruption, reputation risk, and above all, provide a safe and reliable environment for our inhabitants. And if you look at just these pointers and try to align them up, and you'll find that maybe not in all cases, at least in some cases, it's questionable whether they are consistent. For example, you can ask whether recycling buildings at the end of their useful life, albeit that's probably a very sensible thing to do from a sustainability perspective, is actually resilient. On the other hand, if using sort of low embodied carbon materials such as timber in robust structures that resist very extreme environmental loads, is that feasible? And you could probably convince yourself that not in all cases these are sort of conflicting or mutually exclusive things, but at least in some cases these are competing interests. So just keep that in mind. And again, it's the same exercise, but coming more from a decision maker's perspective, what are the drivers that makes people decide on sustainable construction practice versus resilient construction practice? On the one hand, we hear a lot these days, ESG's corporate responsibility is one driving factor for going sustainable and going low carbon. TCFP reporting and sort of maybe perhaps upcoming regulatory requirements. This will also tie into accessibility of capital for a lot of developers. And there's also market forces, investors and buyers would like to have low carbon development. And these are all forces that are driving people towards sustainable design. On the other hand, for resilience, A lot of the times this is driven by, protecting human well-being, health, and safety. I hate to say this, but a lot of the times this comes in the form of code compliance. For a lot of forward-looking business owners, it's about protecting critical assets, content, business continuity, and reputation. And there's also a market demand for resilience, disaster resilient assets. And I hate to say that this is probably less matured in Canada compared to some of the more disaster-prone regions in the world, such as Japan, Chile, Taiwan, and the Philippines. But in those countries or regions in the world, you can actually see resiliency or disaster resiliency as a marketing tool for a lot of developers. It's that developed in those economies. So, the point is that what I'm trying to make here is that a lot of the factors driving decision towards sustainable design practice or resilience are not, there's more difference than commonalities between these two. But that's not to say that, all of them are mutually exclusive. For example, things like TCFD will incorporate both elements of sustainable design and resiliency. But by and large, I think we're not there yet as a society for decision makers to say that, oh yeah, it's a no-brainer that we must consider both. I think by and large, a lot of decisions are still being made, one reason or another, but without sort of the realizations that there will be impact on both resiliency and sustainability. So this kind of, the reason why I have these long contextual setting slides is that before I even get into embodied carbon, it's because I want to highlight that there is a greater underlying theme behind all this, is that there should be a more holistic decision-making framework that incorporates both of these aspects when dealing with our built environment. A lot of times we'll find competing interests, and that means we'll have to balance trade-offs, and that's just the reality of things. And if we don't do that, the alternative is that we may achieve neither. And that's exemplified by this photo that I have, which I really like. It's basically a collapsed building, industrial building by an earthquake right after it's gone through a full energy retrofit. So focusing back on sort of the topic at hand, which is embodied carbon, I kind of wanted to start with the phrase that we hear very often is the greenest building is the one that's already built or that already exists. And of course, you can ask that, is that true? Now, just to be fair, and I think in a lot of cases, this is actually true, but at least I can contemplate some examples that this isn't true. This doesn't hold. And as a society, I think we obviously want to reuse our buildings, but doing so blindly may actually leave some of the physical vulnerabilities unattended, leading not only to poorer building performance in terms of safety, but also it may defeat the purpose of reusing the building in the first place. So I think we must be careful about that. And in particular, I'm talking about the embodied carbon that is associated with repair and replacement of damaged infrastructure or assets after a major disaster. It's something that is not commonly accounted for when we're doing our life cycle cost analysis. And over the last decade, I would say more 5 or 10 years, multiple studies have tried to actually quantify the carbon cost contribution coming from recovery of major disasters. And of all the literatures out there, I think there's a wide range, putting it anywhere between 5% to 40% of the total pre-service embodied carbon in a single building. Most of these come from earthquake studies, so I would say that. And the median sort of estimate in these kind of studies is around the 20% mark. Now, of course, keep in mind that these are average quantities weighted by the probability of occurrence, because a building may or may not suffer huge damage or collapse during a given event, or the event may or may not occur. So, after we average through all the possibilities, this is the number that comes out. But keep in mind that when a major event does occur and you get collapsed buildings, the embodied carbon to replace a building is pretty much 100% of the pre-used carbon, plus an additional because you need for demolition and debris removal and so on. So, this is kind of an example that's used often, but this is the Christchurch earthquake in 2011. It's about a little bit over a decade ago. So this is a picture of the downtown area. show after the Christchurch earthquake. Actually, I think this is taken at the 5 years after the initial event, where most of the building was demolished. So 70% of the CBD has actually been demolished because of the earthquake, not because they collapsed, but because it was deemed impractical to actually repair. So demolition of the event led to basically pretty much 100% embodied carbon costs, if you think in the perspective of the building that's being replaced. And obviously there's a lot more I can talk about Christchurch, but the point here is that when an earthquake happens, this will incur basically a tremendous carbon cost to the society. And it's so big that perhaps a substantial amount of our effort in trying to curb and reduce carbon emissions elsewhere will be undone. And that's something to be thinking about, So another example is that, that always comes up when we talk about this topic is, the tsunami and earthquake series in sequence in Tohoku, again, in the year 2011, which was not a great year for disaster resilience. So most of you has probably seen, like online videos of the tsunami just wiping out everything in its way as it makes shore. And the fact is that the post-tsunami, basically reconstruction of the residential sector alone in 2011 emitted about 26.3 million tons of CO2. And to put that in perspective, that's about 2.1% of the total national emission in Japan. And I did a quick lookup. That's equivalent roughly to just above 12% of annual emission here in Canada, just from the single year. This is excluding industrial, excluding commercial reconstruction, and only in 2011. So that gives you a perspective what these figures might look like. So the previous couple of slides consider only earthquakes. In fact, talking climate change these days, extreme weather events such as hurricanes, floods, wildfire, which is something that's not unfamiliar in BC, can add further contributions to this carbon cost. So this slide actually shows a picture of the aftermath of Hurricane Laura in one of the buildings. Some of you might recognize this building. And you can see severe damage in the building envelope and curtain wall systems. And in fact, there are pictures showing interior damage, basically a havoc. The wind breached the building envelope and caused further destructions inside the building as well. So, flood and extreme events like this are relatively less severe. I mean, this one caused, I think, probably insured damage of $12 billion plus and minus, comparing to, you're probably looking at $200 billion US dollars for the Tohoku earthquake and tsunami. But still, they are more frequent, like hurricanes happen every year. They're more frequent, and therefore the bill, as far as embodied carbon is concerned, may actually be even bigger coming from climate hazards because, they may be getting more frequent as climate change makes its course. And an interesting point I want to kind of make here is that the damage in the building envelope that you see in this picture could have also impacted the operational carbon because probably, part of the insulation system of the building. And, if you think on the flip side, by considering both climate resiliency and emissions holistically, you could have addressed both problems. So this kind of brings me to sort of the main points that I want to discuss in this presentation, which is I think there's a need for us to quantify embodied carbon impacts coming from major natural disasters to inform decisions. On the one hand, I think decision makers should at the very least understand at a quantitative level what this embodied carbon contributions mean to the emission strategies and targets. And maybe at the very least, this may shift sort of the baseline estimates of a lot of our existing assets. And secondly, maybe on sort of the silver lining in this is that I think there's genuine opportunity in to embed both resiliency and sustainability thinking into a more holistic decision framework in order to make decisions about our built environment. And sort of the rest of the presentation, I try to touch on these 2 points and really, if at the end of the presentation, the takeaway is that, there should be more exchange between those of us who work in resilience and those of us who work in sustainability. And I think I would have achieved, my purpose. So the next part of the presentation, I probably focus on some of the tools that we use to quantify these kind of impacts. And And for those of you, who are engineers, well, first of all, as a professional working on basically resiliency and physical sort of risk, our work intersects with embodied carbon mainly through the FEMA P58 standard. And I think for some of the engineers in the room, this is not unfamiliar, and others might not be so. So I'll probably give a brief overview of the tools anyway. So we mainly use it in the context of predicting embodied carbon and embodied energy impacts associated with building damage that could contribute to the total life cycle cost. So I've shown here on the right also the ISO, which is essentially the standard for life cycle analysis. And the main interactions that we deal with on the practical level, or in practice, really deals with region-specific or region-appropriate data, because the FEMA standard comes with a standard database that is based on US data. And in order to use it sort of in other regions in the world, we need to kind of find region-appropriate data. And that's one point that I can further elaborate as I go on. But yeah, the FEMA P58. So it's a lot of you might know, this is initially started as a probabilistic methodology for assessing earthquake damage and loss. The method functions at an asset-specific level, so on a single building. And it just so happens that the methodology that's developed to account for damage and loss in a single building is actually very similar to the way one would account for embodied energy and carbon costs. So in the latest edition of the FEMA P58 that was out in 2018, there was a methodology that's included that would basically allow us to quantify these environmental impacts in a probabilistic way. So in the context of earthquake, I'm going to walk through what actually happens if somebody says, we estimated the embodied carbon follow the FEMA P58 methodology. So we will start with basically the seismic hazard at the site of interest. And the next step is that from the seismic hazard, we define the level of shaking and apply it to the building. So we carry out engineering analysis on the building structure. And from those, we derive on a component basis what kind of damage we might experience from the earthquake. And this is essentially like doing accounting. We look at different types of components, we count the amount of quantities, each component can be damaged to a certain extent, and we just repeat this process. And at the end of the day, what we'll arrive at is that a description of the damage state of the building in terms of each individual component. And from those, we can derive sort of damage appropriate repair measures. The repair measures will change depending on the extent of damage. And these will include, labor and material, and you will have material, you have transportation of materials onto site, you'll have people working on it, and, energy consumption while you're on it. So each one of these repair activity would have, sort of a list of, emission items. And by summing them up, you can characterize how much emission in terms of embodied carbon is incurred per repair activity. And if you sum up each repair activity for each component that's been damaged and doing it for all components and so on, you can quantify essentially the total emitted carbon from a damaged building, or to bring a damaged building back to its pre-earthquake state. And this is how we do it. And I should mention that the default database coming with the FEMA P58 is based on the USCIO database. I'm always not sure whether I should pronounce this UCO. But anyway, but that's primarily US-based data, which is only appropriate, for constructions in the US. But however, by no means this is a limitation on the methodology itself. You can always, substitute this with sort of more region-specific data that you think is more accurate if you want to. So all of this process, starting from defining the seismic hazard, doing the earthquake simulation, all the way down to quantifying the embodied carbon and embodied energy impact in the building, we repeat these thousands of times to generate a probabilistic sort of description of the embodied carbon in the post-disaster recovery. And that becomes a final output or metric that you can incorporate into sort of a fuller life cycle analysis. And that will represent sort of the post-disaster rehabilitation contribution of embodied carbon and energy that you would include in the life cycle. So This is perhaps a little bit of a deviation from the main point, but I do want to mention that although the FEMA P58 method is initially developed for earthquakes, it doesn't actually, it doesn't have to be limited to only earthquake hazards. In fact, it could be readily extendable to all these other kinds of climate-related hazards, including hurricanes, extreme storms, floods, and so on. And what you would do is basically replace the engineering analysis that you perform for earthquakes with a equivalent, procedure for other types of hazards. For example, in wind, you might look at aerodynamic analysis and windborne debris analysis. For floods, you might look at hydrometeorological models or hydrodynamic models. And at the end of the day, all you're trying to do is basically resolve the causal relationship between environmental loading and damage. And from that point on, everything unfolds exactly the same way as you would do in an earthquake analysis to capture the embodied carbon or any kinds of resilience performance metrics. And to the learned eye, probably the experts in this room, you will know that I condensed half a dozen steps into this very simple diagram. So don't take it as being a fair or representative schematic of how this multi-hazard analysis should unfold. But in principle, this is how it's done. So, we can do this kind of analysis to capture the embodied carbon contributions from other types of hazards. So in sort of the next set of the presentation, I do want to present some examples of how, FEMA P58 is actually put to action in practice. And the first example that I want to show is basically a project to develop design guidance for seismically resilient and sustainable tall residential buildings in BC. And this is supported by BC Housing. And obviously the project scope is for seismicity in BC. So we're looking only at the construction sort of archetypes that occur commonly in the West Coast. And we're focusing really on just new buildings that will be designed to the modern seismic code. So the resilience aspect of this buildings will manifest sort of in the minimization of physical damage and downtime of these metrics, which we deal with on a regular basis. And obviously these will translate into lost homes for people who live in them, right? So that's a huge social issue as well. But on the other hand, the sustainability metrics that we look at are on the embodied carbon, embodied energy cost associated with the earthquake recovery, quantified using the FEMA P58 method. And in this particular project, I would say to the extent possible that we have recalibrated the component database in the original methodology to reflect sort of region accurate costs in BC and in Canada. And this includes both sort of the repair cost consequences as well as sort of the carbon cost. And this is, I would say, one of the most time-consuming part of the project. So here is an example of what the FEMA P58 process might spit out at the end of the day. So I'm showing one of the building archetypes that we looked at, showing the average embodied carbon impacts in metric tons under 7 different earthquake scenarios of increasing intensity. So for those of you who are not engineers, we typically describe earthquake intensities from sort of the probability of exceedance in a fixed amount of time. So in this particular case, we assume a 50-year useful life, and different events we define based on how likely during that useful life shaking intensity will be exceeded. So just for reference, the 2% in 50 years probability is basically what the building code stipulates as the basis for design today in Canada. And the 10% in 50 years is what most insurance companies will use as the basis for screening risk for obviously insurance policies. So in this example, you can actually see the breakdown of embodied carbon contributions coming from different components as well. So in this particular case, this is a residential structure. The biggest contributor in this particular case comes from interior partitions. These are mostly your typical gypsum board partitions in a condo building. Which because it's cementitious, they're heavy in embodied carbon. And one of the things is that conventional drywall are actually quite easily damaged in an earthquake. So the second largest contributor comes from repairing of structural elements. So this will be the concrete wall elements, concrete column elements that are damaged or cracked during the earthquake, plus also the replacement cost of the building in the case of a total loss. Now, just to clarify, maybe some of you are not used to looking at these. So the values that I'm showing on this figure, these are average values. So in other words, they are consequences weighted by the probability of occurrence. So for example, if you look at the yellow contribution in one of these bars, that is associated with the total replacement of the building. In other words, the building either collapsed or it's damaged beyond repair. You have to basically take it down and build a new one. And in reality, that would have incurred 100% of the embodied carbon as the pre-use case because you're replacing it. The reason it's not 100% here is because it's weighted by the probability that most of the time collapse is rare in these new buildings, even under very extreme earthquakes. And therefore, this is an average value, but this is by no means, you shouldn't interpret it as, there's no scenario where you will realize this average value. What you will use is probably, apply to the entire building stock of similar construction to estimate the average embodied carbon contributions. But if an event actually unfolds, then the situation will be very similar to what you saw in Christchurch. A lot of buildings might suffer total loss, and for those buildings, it will be total loss. Other buildings might suffer nothing, and in this case, they either were lucky or you would cause no embodied carbon. But on average, these are the values. So another thing that we can do with these types of analysis, is that we can definitely change the design performance objective at the upfront to see and observe what the impact is in terms of the loss metrics, recovery metrics, as well as the environmental emissions. And this is exactly what we have done for this particular study, is and on the screen, it's the same building that you saw on the previous slide, but this time we've compared 3 different design bases. On the very left is the base case, which is basically what you will get by designing a building to the NBC 2015 today. And you will get a building that meets life safety, but may not be usable after a cold level event occurs. And this is reflected in the significant cost and downtime that you see in the red and green bars there. On the other hand, we can propose a more robust structural solution and observe that the loss metrics substantially reduce across all 4 different metrics. However, they may still be substantial. And finally, if we try to design the most resilient structure possible by strategically upgrading the structural and non-structural components beyond what would be otherwise required by code, you can actually end up with a building that has almost no loss at all. And the cost of doing these additional steps typically ranges from 1 to a few % if you're talking about a new building, in the context of a new building. So, and we're hoping that, we can produce these kind of analysis that produce a very quick guidance for decision makers to at least start exploring these beyond code solutions, as I think, they probably require as we move on with climate change and disaster resiliency. So one of the purposes of this report is to produce these very quick guidelines and for BC housing to use, but it's for general developers, but this does focus mainly on residential buildings. So another project that I want to touch on is some of the works that we have done in collaboration with the University of Bergamo in Italy. A central theme of the project is the so-called life cycle thinking approach for combined energy and seismic upgrade of deficient building stocks. And this framework aligns pretty well with sort of the holistic approach to the built environment that I was talking about in the earlier slides, which considers both resiliency and sustainability. The project considered an array of environmental metrics. So in other words, not just embodied carbon. Actually, the emphasis is probably more on the energy retrofit that will reduce the operational carbon in this particular case. So one of the applications that we used, that we looked at for this sort of holistic design framework is basically the exterior envelope upgrade of these quintessential sort of post-World War II structures that were erected in massive quantities after the war because they need to accommodate, the booming population. And for a long time, the Italians know their basically deficiencies in terms of energy consumption and in terms of structural integrity. And our approach to solving this issue was basically to generate an exhaustive list of structural upgrade solutions that will work in unison with the external energy upgrade. And on this picture, you can see some of the concept on the structural and architectural upgrades that were proposed for these type of structures. So as part of this exercise, we generated sort of for every single upgrade option that we generated, we perform a full performance-based seismic analysis on it. And I show only 6 retrofit options, but there are a few more that I didn't show for the sake of space. Essentially, going a brute force analysis on each one of these upgrade options and quantifying with these very simple sort of stakeholder business case reports, what are the impacts of each of these upgrade solutions in terms of loss, in terms of downtime, and in terms of embodied carbon. And you can see that the embodied carbon can be quite substantial if you don't do anything. It's more than 50% of the pre-use case. That's the figure on the very right. But I would say this, that probably the embodied carbon metric, although it's important, again, it's not the main, it's not a deal breaker in this sense, because a lot of the decisions that drive these kind of upgrades actually governed by the need to have the energy upgrade and the seismic upgrade. But nonetheless, it is an important factor to be considered. And this example demonstrates that it drops out quite conveniently from the analysis that we do. And there's no reason why it shouldn't be used as part of the decision making. So a final sort of example that I want to touch on, which we use the FEMA P58, is a sort of a joint research project between Kinetica Risk and the University of Toronto on a resilient mass timber building. Now, I don't think I have to preach to this group about the benefit of timber construction. and actually, I think the opposite happens in a lot of cases, that I was preached about the benefit of timber constructions. However, I believe I did mention in the beginning of the presentation that timber constructions do have their own issues when it comes to seismic resiliency because of their lightweight and lower stiffness compared to concrete and steel. And furthermore, one of the problems with timber constructions in seismic areas is because most of the nonlinear behavior, in other words, the damage, occurs in the joint in timber construction. And these are not necessarily always easy to inspect, assess, and repair. So one of the goals of the projects that we are doing is basically propose an alternative mass timber shear wall structural system with improved seismic performance through the use of supplemental damping elements embedded in timber shear walls. So this is a schematic of one prototype building that we came up with, 12 stories, with timber shear walls embedding these damageless dampers. So the idea is that in an earthquake, these dampers will basically dissipate the energy and thereby, number one, lowering the seismic demand on the rest of the structure, and number two, protect sort of the connection elements that will be easily damaged, so to eliminate repair that would be otherwise required. So, through analysis, we're able to demonstrate that this particular scheme would reduce seismic demands by about 30 to 40%. And that translates directly into a reduction of loss and a reduction of embodied carbon. And this is very easily done and through exactly the same FEMA P58 procedure. And in this particular case, because the prototype building it's very well known what the component in terms of structural in the building are, we were able to drive very easy to use and fairly accurate predictions of embodied carbon impacts just based on running these analysis. So you can use them without running necessarily the full performance-based analysis to quantify, at least at a high level, what the embodied carbon impact would be. Now, again, I want to say that from an emissions perspective, I think the embodied carbon savings in this example is likely to be less important than the fact that this is a mass timber construction. But nonetheless, again, it's a well quantified metric that can be readily incorporated into the decision making, and there's no reason why we shouldn't do it. So, I wanted to kind of conclude at this point of my presentation, and if there is a few takeaways, I try to summarize it in a few points. And firstly, I think, hopefully it's clear to you that embodied carbon emissions caused by post-disaster rehabilitation of damaged assets is a significant part of the life cycle carbon cost. And I think at the very least, it's worth quantifying and considering in our emission strategy. And number two is that we have existing engineering tools that we use, namely FEMA P58 procedure that allows us to quantify this, not just for earthquake, but for other types of environmental loading as well. And finally, I think this is probably the most important point that I want to drive home, is that I think there is a need for more professional collaborations between those of us who work on resiliency and those of us who work on sustainability to develop more holistic approaches to decision-making in our built environment. Now, this could include, things like better databases that facilitate the type of calculations that I presented in the Canadian context to allow more people to incorporate it into decision-making. Or this could be in the form of, just regular project planning meetings or stakeholder meetings to make sure that we bring to the surface all these different aspects of building performance so that it's upfront and clear in the beginning of the planning cycle. So finally, just before I stop talking, I'd like to acknowledge the CIF Vancouver for giving me the opportunity to present on this topic, and BC Housing for the support for the residential building project, as well as my colleagues from the University of Bergamo and University of Toronto, particularly Dr. Embodied and Dr. Chiara Passoni, for supplying some of the contents that I talked about. And thank you very much.
Thank you, Jack. Yeah, that was excellent, really good. It was really nice to see some numbers against the embodied carbon for rehabilitation. And it looks like lots of people agree, because already I can see several hands on the participant faces. So maybe I'll just open it up to the floor. So if you have a question for Jack, please do mute yourself and take it away.
I guess the first question came in from Jeremy. Do you want to go first?
Sure. Thanks. Thanks, Jack. That was great. So I think you kind of answered it at the end, but I asked it when you were presenting on wind, floods, and earthquakes. I mean, as probably everyone in BC is thinking about, can it also be used to quantify risk and resilience for wildfire?
Yeah, that's a great question. I think in principle, probably, but the characteristic of wildfire damage is that a lot of it is driven by, the close proximity to the home. And unlike earthquake, wildfire damage, if you look at insurance data, tends to be all or nothing. And I think there are some pictures that you can see from the BC wildfire that, one house is completely damaged, one next to it is perfectly okay. So, from a component perspective, probably might not be worth quantifying, if half a building is damaged, what happens to it. So, so in that regard, I don't think you have to move to the FEMA P58. There's a lot of insurance analysis tools out there. Most CAT model vendors will have wildfire models that would tell you the probability of damage. And of course, you can use that to account for the embodied carbon emissions of wildfire. Just that not at a component specific level, which is what the strength of the FEMA P58 really is. I hope that's clear.
That is, yeah, thanks.
Yeah.
Can I go next? I just sent in my question. Thanks for the presentation, Jack. It was really great and very insightful. So my follow-up question to the mass timber study that you have done is, have you looked into the recently built or under construction mass timber high rises in the West Coast or in general, and have they incorporated any of these suggestions that you had regarding the connections and resiliency to not getting damaged during earthquake? And another question is that you mentioned that you have modeled a lot of alternatives and looked into the different variables, including embodied carbon. And I wonder if you have use any parametric design tool, or is there something like that available? So that's it. Thank you.
Yeah, so I think the first question is really about the mass timber building. Yeah, we haven't applied to some of the ones that are, I know, some of the tall buildings are currently going up in BC. I mean, the project by and large is still ongoing. And our point is basically to develop a system that is economical to build, that is modular. And embodied carbon, frankly, is one of the many metrics that we evaluate the performance with. But I mean, I don't see why not. I guess that's the question.
Well, my question was more on have you looked into the connection designs and have they incorporated the type of recommendation for damage-less connections? Or is
Yeah,
that
no,
something?
I think, sorry for missing the point. Yeah, in that case, we have looked at some of the connection design elements, probably more so in the context of the system that we're proposing, which I would say might not be commonly applicable to all kinds of timber constructions. That's what I would say. And I think really in our context, the purpose really is to try to prevent damage in the connection, or rather than trying to improve it, because anytime we have to go in and fix a connection, that means downtime and losses and embodied carbon, amongst other things. So we rather, if we can, try to prevent damage in the connections and trying to basically handle seismic load through other means. So that's sort of the scope that we have defined.
Right, thanks. And then I wonder if you could just give a quick answer to my next question regarding the parametric design tools, if there are anything available.
Yeah, so that's something in development. So it's obviously the project that we're working with BC Housing on, the end goal is to basically provide these parametric design tools so you don't have to go through these performance-based analysis, which is really daunting for somebody who doesn't handle this on a regular basis. And yeah, the idea is that there will be a few very large targets of design that we either increase the structural resilience to a certain point, and this is the cost, and that's what kind of reduction you'll be looking at in terms of carbon emissions, in terms of cost savings. Yes, and those would be published, I believe, later this year.
Thank you.
We also have a question from Veronica. Veronica, would you like to ask Jack directly?
Yeah. Hi. So yeah, my question is about how do we request this to be incorporated into the normal scope of services? Because like this is part of the whole life cycle of the building.
Yeah.
And when you design for circularity, you're meant to consider durability, flexibility, adaptability, and all of these resilient measures are part of that. So I would even say that if you have to exceed a bit your carbon budget to make a more resilient building at the very beginning, then go ahead, because that's going to save you a lot of repairs. And forget about the repairs, just people who don't have somewhere to live or whatever further down the line. So how do we make this part of the conversation? When do we raise it up? Like, if we do life cycle assessments, do we say, hey, I want this to be incorporated like as part of our team? How do we put it forward?
Yeah, I think in terms of timing, probably the earlier the better in terms of the planning stage. I think this is where we should be brought in. I think engineers and like people who kind of work in the same area that we do would bring this kind of capability into the team. You're welcome to reach out if you want, but I think generally in terms of timing, the earlier the better, because this could affect a lot of the decision making downstream. And I think I don't want to sort of generalize, but I think a lot of the usage of the FEMA P58 seems to be somewhat of a passive thing. I design a building, and at the end of the day, I want to prove that the design was great, so I run the FEMA P58 to kind of reverse justify what I did. But I think really the value of this methodology is as a planning tool, and it should be introduced into the sort of the decision-making cycle as early as possible.
Thanks, Jack. If we go to Kevin next, who's got his hand up there.
Awesome. So in your experience, Jack, have you found that preparing these structures to kind of mitigate the damage post-disaster requires additional upfront investment in embodied carbon? So like, do we have to increase the structure, which obviously has an embodied carbon cost associated with that, to mitigate that post-disaster impact?
So just let me clarify, are you talking in the context of a new building or in an existing?
Yeah, I'm looking at a new building. Like if we were to try and go through this process for buildings we're creating today,
Yeah.
do we weigh these things out?
Yeah, no, I wouldn't say that there's zero carbon cost, but I think it's definitely not as linear a relationship as you think it would be. Typically, the upfront premium is very small on an overall scale of things, because I think what we're trying to improve is trying to prevent sort of the most common elements that are costly from being damaged, and that could meaning simply as mounting some of the mechanical systems that are very prone to seismic loss, or choosing a smarter interior partition system. It's not about throwing more concrete at the structure. Really, at that point, is you're trying to actually look at what is your cost driver, both in terms of financial loss or in terms of embodied carbon. It's the same, and trying to mitigate those specific things. So yeah, I would say in my experience, the upfront cost is fairly minimal. Like I said, in a new building, it's not uncommon to see maybe 1-2%. In some of the cases, maybe up to 3-4%.
Awesome, thank you.
I think just to jump in before Warren here, that was my primary question and takeaway. The slide that you had where you were comparing the 3 case studies, it looked like upgrading the shear walls did very little to change the damage following an earthquake, but upgrading those non-structural components, that was where the real achievements were. So is that just fixing down mechanical equipment better, or are we kind of doubling up on all of the connections across the building?
No, I think, yeah, it's both. It's I think sometimes it means smarter. So in the residential context that I was talking about in that slide, you saw that the biggest contribution coming from interior partitions. So if you have a smarter system that allow the interior partitions to slide during an earthquake so that they don't crack because of the fixed boundary conditions, you could automatically save a lot of repair costs and subsequently embodied carbon. So smart things like that, rather than trying to beef up the partition system as much as you can, because you're fighting an endless battle with earthquakes. And that is in the residential context. And I think that's probably one of the building types that have the least amount of mechanical equipment. If you're talking about a hospital, for example, most of your building cost is in the MEP systems and in the equipments inside the building. The structural system is almost nothing, like 20% of the total cost. So definitely, I think I can probably say that in general, for most buildings that we encounter, it's about sort of looking at smarter connections and identify where the cost drivers are. And a lot of the times they're in the non-structured system.
Great, thank you. And now I'll pass over to Warren, who's patiently waiting.
Oh, no problem at all. Enjoying the conversation very much. You touched on a few different times in my questions around existing buildings, and I think everyone here probably agrees a holistic approach is very much needed. I'm thinking of the drivers and really the trigger points for moving retrofit work, which is in desperate need on a wide scale basis to move forward. Have you been involved much in integrating some of this work with capital planning work and renewal periods, and also considering functional obsolescence and those kind of issues as well? And how, if so, how have you found that has come together, and what's really driven that process?
Yeah, no, that's a great question. I think it's very relevant, and I would say yes, I have. I would say that most of the time, the sort of the driving force behind it was more so related to the resilience aspect rather than sustainability. And like I said, in my experience, the practice seems to be encapsulated in their respective silo quite a bit. But I would say that from my experience, I think it really depends on how determined the decision maker or the building owner are in terms of moving forward their resilience target. And I had, for example, like one of the examples that projects that we have been involved with was basically the parliamentary precinct of Canada modernization project. And in that particular example, the asset owners were extremely forward-looking. And they understand the risk implications of the type of upgrade that they do today versus something that they do in 20 years. And that's one of the reasons they asked us to do these, the full sort of suite of performance-based analysis in order to guide the decision making. This is projects that will happen over the next 20, 30 years, and they're looking at it today. So I think, it really depends on how determined the decision maker is trying to push these initiatives. And then obviously in that case, they've got a very low tolerance for downtime and damage. And I think it also helps that there is a special department dedicated only for this purpose.
And as a follow-up to that, and looking at that specific example, were they considering their overall capital plan and realizing, like, very commonly we will see groups move ahead. Let's say they get a VFA or some other report, some capital planning report, we may have put it together, and they're based on like for like. And the thinking isn't from a portfolio manager necessarily, okay, let's just get this done because that's what we have budgeted for, but they haven't integrated all these things in together to look at it more holistically. I think we have to very much collectively educate the industry in requiring that. That's not just a nice thing. That's very much needed, whether it be energy driven or seismic or whatever. And very often we see one of the components left out. So I was wondering if your experiences have been consistent with that.
No, I would very much concur and attest to that. I think in this particular case, like I said, there is a group within the parliamentary precinct that's looking at this as a holistic portfolio management problem. And underneath them, there will be separate projects, but I think there is at least a collective will and an integrated framework for them to make decisions on each one of the assets in the portfolio. And that really helped, drive some of these bigger initiatives that fuel the integral thinking that is needed in this type of project.
Okay, thank you very much, Chuck.
Ron.
And I think we've just about got time for Matt's question.
This should actually be a relatively quick one. I'm just curious if the modeling is detailed enough to look at, with respect to the MEP systems, whether it's detailed enough to look at where those systems are actually located in the structure and how that affects the outcome of the model.
Yep. Yeah. So the quick answer, is in principle it is, but in practice is rarely done down to the level of detail. Like we don't identify, for example, an individual air handling unit on the southwest corner of the building. We can, but we don't usually do it. And the reason is because very rarely actually 100% of the time when we're dealing with existing buildings, collecting that level of information down to that level of detail is a huge endeavor. And I have never personally encountered a case where the building owner has all that information available to us.
I was thinking more along the lines of the commercial sort of structures where the MEP systems tend to be on the roof, where they would experience the highest seismic response versus.
Yeah, in that case, then yes, we typically in practice, the most common thing that we do is typically segregate it into story levels. So in each level, we'll have different content, different population. That is basically the typical practice. But we can go into further refinements within a story, but we don't usually do it because of the limitation and quality of information that's available. Yeah.
Just a side note there, Jack, most complete capital blends should have all that information in it. So it should be readily available for you.
Yeah, no, I think for new buildings, you're exactly right, Warren.
No, I'm talking about existing buildings.
Yeah, I think it's very difficult in a tall order for even for some of the very forward-looking owners that we have to actually characterize individual building contents at a specific location within the building, and that's a very difficult thing for them, at least in the cases that I've dealt with. But it would be great if that's available.
Great. Well, thank you all for the questions. I think we're just about out of time. So I would just like to thank Jack again for coming along today and sharing his knowledge with us.